Continue on physical chemistry, chapter 18. We're in section 15, which is the last section in chapter 18. Now we're going to talk about approximation methods. See the approximation methods handout. So we're going to talk about particle interaction prevents exact solutions to Schrodinger equations. So we have approximation methods. So one is the variation method. So we're going to say our energy for our trial solution is going to be integral of phi star Hamiltonian phi d tau, which is greater than or equal to the energy of the ground state. GS would be ground state. So remember, h hat or h caret is the time independent Hamiltonian. Phi and phi star, these are normalized. So phi and phi star, they're trial functions, not angles like in the previous section. And our energy for our trial solution is going to be greater than or equal to the energy of the ground state. So ideally, our energy for the trial should be equal to the energy of the ground state. So if E equals isn't normalized, then we're going to have to change the integral. So remember, the integral of the absolute value squared of n times phi d tau is going to be equal to the absolute value of n squared times the integral of the absolute value of phi squared d tau. And that's going to be equal to 1. That's what normalized means. So we're going to solve for capital N squared, absolute value. So we get square the absolute value of n is going to be equal to 1 over the integral of the absolute value of phi squared d tau. And that's going to be equal to 1 over the integral of phi star phi d tau. So we say n is the normalization constant. So we get the integral of phi star times the Hamiltonian phi d tau divided by the integral of phi star phi d tau. And that's going to be greater than or equal to energy of the ground state for any function. Now if it's already normalized, the denominator is already equal to 1. So the numerator is all we need. So the energy of ground state is going to be 0.125 h squared over ma squared. So we get psi is equal to the square root of 2 over a times sine of n pi x over a. So let's say that our trial function for psi of x, we get psi of x is equal to x times x minus a. Well, first we need to show that it fits the boundary conditions for the particle in a box. So we have the limit of as x approaches a of x times x minus a, and that is equal to 0. And the limit as x approaches 0 is x times x minus a. That's equal to 0. So it does fit the boundary condition. So we get psi star Hamiltonian psi is equal to x times x minus a times minus h squared over 8 pi squared m times the second derivative with respect to x of x times x minus a. Now in this case, psi is real, so psi star is equal to psi. And likewise in this case, the function and its complex conjugate are the same. Because like I said, if it's real, then it's equal to its own complex conjugate. So we get the integral from 0 to a of psi star Hamiltonian psi dx. And that's equal to minus h squared over 4 pi squared m times the integral of x times x minus a dx. And that's equal to minus h squared over 4 pi squared m times this whole quantity, the integral from 0 to a of x squared dx minus a times the integral from 0 to a of x dx. So we separated these two out. That's going to be equal to minus h squared over 4 pi squared m times a cubed minus over 3 minus a cubed over 2. That's going to be equal to minus h squared over 4 pi squared m times minus a squared over 6. And that's going to be equal to h squared a cubed over 24 pi squared m. Now that's just the numerator. So it's not normalized, so we have to take the integral of the bottom too to normalize it. So we got the integral from 0 to a of psi star psi dx, and that's going to be equal to the integral from 0 to a of x squared times x minus a squared dx. And that's going to be equal to the integral from 0 to a of x to the 4th dx plus a squared times the integral from 0 to a of x squared dx minus 2a integral from 0 to a of x cubed dx. So we get a to the 5th over 5 plus a to the 5th over 3 minus a to the 5th over 2, and that simplifies to just a to the 5th over 30. Now we can divide the numerator by the denominator. So our trial function, e prime, we get the integral from 0 to a psi star Hamiltonian psi dx divided by integral from 0 to a of psi star psi dx. So E trial is going to be equal to h squared a cubed divided by 24 pi squared m, all that divided by a to the 5th over 30. Rearrange it, we get 30 h squared a cubed over 24 pi squared ma to the 5th. Cancel a few things out, we get 5h squared 4 divided by 4 pi squared ma squared. So that's equal to 0.127 h squared over ma squared. So now we find our percent error. The expected value was 0.125, so we take 0.127 divided by 0.125 divided by 0.125 times 100%. We have 1.6% error. So that's actually too much for quantum mechanics. So we want to try a better approximation method, like x squared over x minus a squared is equal to psi of x, or something like that. So the second approximation method is perturbation theory. So remember, the variation method works for the ground state only. The perturbation method, it'll work for the ground state or excited states. Now, the reason we're doing this, remember, is sometimes Schrodinger's equation, it can't be solved exactly. The potential energy gets too complicated when you have many particles and so on. So we have the Hamiltonian times psi of n is equal to the energy of n times psi of n. So now we get Hamiltonian, oh shoot, I forgot what that's called. Psi of n equal to the energy of n psi of n. Notice the not there. So we'll say that's our exact value. This is our approximation. So we get the Hamiltonian is equal to this exact value plus the perturbation. So we get En is equal to the integral of psi n star Hamiltonian psi n d tau. So just like average, this gives you average energy. And of course En is going to be En 0, En 1, En 2, En 3, etc. So we say that En1, that'll be our first order correction, which should be the largest correction. And then En2, that should be your second order correction, which will be smaller than that. And then each successive correction will hopefully be smaller and smaller and smaller. And that's all for that section.